going to have the last talk of the boot camp, which will be the second part of Kamalika's talk today.
Okay, thank you very much. So, yesterday I talked about nearest neighbors and, some of the more basic and classical stuff about classification and regression. Today I'm going to change tracks a little bit, and I'm going to talk about some new stuff we have been doing on nearest neighbors and adversarial examples, and also more general adversarial examples, more generally adversarial examples for non-parametrics. So this was, again, this was yesterday. Today we are going to change tracks a little bit. Okay. So what are adversarial examples? You guys have, I'm sure you guys have seen this demo. You have an image of a panda. You have a neural network who's absolutely confident it's a panda. And then you add this, right? 0.007 times this, and to you it looks like a panda. And to, I guess to all of us, it looks like a panda, but now your neural network is super confident that this is a given, right? So, and I mean, this is not the only demo. You have seen many such demos, like, like stop signs, you put stickers on it, and then suddenly cars think it's an yield sign, and, all this sort of stuff, right? So that's adversarial examples, and, I am sure I'm missing out a whole bunch of citations here. Segedi et al. 2013, Goodfellow, this particular picture is from the Goodfellow et al. 2014 paper. One interesting thing is that actually these kinds of attacks were considered by Chris Meek and Daniel Loud way back in 2005. So it's actually pretty old, and it has seen a resurgence recently. So those are adversarial examples, right? And there's another example. You will see stop signs like this in Berkeley quite a bit. Stop war, and then if you have a self-driving car, it will mistake this as a yield sign or something else, right? And what is going on over here is you have some sort of test input and you slightly modify it, right? So to a human this looks like it's basically imperceptibly slight, right? Like it's a slight modification, and then what happens is this causes misclassification, right? The other interesting thing is that not only is this a slight modification, it's a strategic modification, right? So if you just do a random slight modification of your stop sign, your classifier will be fine. But if you do a modification in some specific strategic direction, then this is not going to be the case anymore. Okay? And many classifiers are vulnerable to adversarial examples, like a lot of neural networks, even some classical things like nearest neighbors and decision trees. They're really vulnerable. And kind of the current state of the art is that there are many attacks. There are many defenses which tend to be broken every so often, and there are also a whole bunch of certifiable defenses which prove that things are certifiable. There is some understanding on why these examples exist, and however that's somewhat limited, right? So I know Sebastian gave a really nice talk on this, but to some extent some of this is understood, not all of it is well understood, why these examples exist. Okay? So what we are going to do today is we are going to, I told you what adversarial examples are. We are going to start out with a statistical learning framework for robustness, and then I'm going to tell you a little bit about adversarial examples for nearest neighbors, and then we will look beyond nearest neighbors to more general non-parametrics. Okay? So remember, yesterday I talked about the statistical learning framework, and just keep nearest neighbor in mind when you are looking at this framework, where you have this metric space. So it's an instance space X, and there's this distance, there's this metric D, and there is some underlying measure on mu on X from which the points are drawn, right? So your X's tend to get drawn from this underlying measure mu, and the label of X is a coin flip. So think about, so for now we are thinking about binary labels, although the analysis, with a bit of messy math will translate in general, but let's think about this as binary just to keep things clean. So the label of X is a coin flip whose bias is eta of X, where eta of X is basically probability Y equal to 1 given X, right? And in the statistical learning framework, what we are hoping to do is you're hoping to get, what we care about is the accuracy, right? So the accuracy of a classifier f is the fraction of times f of x agrees with y, right? And when I say fraction or a probability, what I mean is this probability is over this mu times eta distribution, right? When x is drawn from mu and y is drawn from eta, the y given x, or rather y given x is drawn from eta. So the fraction of times the prediction of f on x agrees with y, that is the accuracy. And in the statistical learning framework, what we always hope to do is find classifiers which have high accuracy. Okay, so now let us look at what happens when we also throw this sort of robustness into the mix. And let's start out with some definitions. Okay, so we define the robustness radius of a classifier f at a particular point x is the distance to the closest z such that f of x is not equal to f of z, right? So basically, the closest distance you have to go so that the label of the classifier changes, right? And very natural definition. We are going to sometimes use this definition, and we are going to denote it by rho of fx, right? And this will vary from x to x, okay? So this is the robustness radius. It will vary from x to x, and high robustness radius means that your classifier is going to be really robust at x, right? At this particular point, it's going to be very robust, okay? Okay, so we have talked about robustness radii. But the thing to notice is that the absolute measure of robustness is actually not that interesting. Because if you have a constant classifier, it's going to be robust everywhere. So you don't necessarily want your classifier to be robust everywhere. What you want is, you want your classifier to be robust at interesting inputs, right? And the way we model interesting inputs in statistical learning theory is through a distribution. So what we care about is robustness with respect to a distribution. And we can define this thing. Okay? Yes?
So if x was misclassified by the classifier, how would you want to define the distance to the boundary?
Yes.
Negative?
So here it would be probably 0. Yeah, okay. According to this definition, it would be 0. Excellent question. Yes, we haven't looked at it. Yeah, that would probably be 0. So the robustness of a classifier at radius r with respect to this underlying distribution is the, basically the fraction of points at which the robustness radius is greater than or equal to r, right? And this high robustness with respect to this distribution implies that, this high value of r implies that high robustness on inputs from this distribution. Okay. And with these, now we can talk about, algorithms and robustness of algorithms. Let's say you have a training data set S sub n, which feeds into an algorithm A, and what comes out is a classifier A of S sub n. Then the distributional robustness of this algorithm A at radius r is this robustness of A of Sn. So the classifier produced by this algorithm at radius r with respect to mu. Remember, mu was our underlying distribution, and let's say the expectation of this as limit n goes to infinity, right? So as limit n goes to infinity, what happens to this, this robustness metric with respect to this distribution? We can also talk about, finite sample robustness. Basically, what happens to this expectation for finite n, right? Okay. And now, so far we have talked about robustness. There is also, your constant classifier is always robust, right? So whenever you talk about the robust classifier, there has to be some discussion of accuracy, right? Some sort of combining robustness and accuracy. And what we do is, we propose this measure called, in which we called astuteness, which combines robustness and accuracy. And it's not just, so we came up with the name astuteness, but other people have actually also come across this measure independently. So there's a paper by Tsipras et al., I think iClear 2019. They have also looked at this particular measure, right? So what does astuteness tell you? So the astuteness of a classifier at a certain radius r is basically the fraction. So remember, accuracy was the fraction of points where the classifier was right. Astuteness is the fraction of points where the classifier is right and it's robust. right? So, not only is it right, but it's also robust, right? So it's like, really quite sharp or astute or whatever. So, so this would be, if your robustness radius was R, this would be a point where it's astute. If your robustness radius was R, if you were over here, then the classifier won't be astute over there because it's correct, but it's not robust, right? And basically what we want to kind of do is, if you want to do robust learning, a goal that we care about is maximizing this sort of astuteness. So we fix R ahead of time, and what we care about is maximizing astuteness. And we can look at things like, of course, again, like just like robustness, we can look at distributional astuteness and finite sample astuteness, and we can define it in a particular way, but usually that in a similar way. Okay. Okay, so prior work, so there has been, again, I should note that this is like theoretical prior work, so there has been a lot of prior work, a lot of theoretical prior work, other than ours, on adversarial examples for parametric methods. For example, Smith et al. Talked about linear classifier and showed that, robustness requires more data. Sebastian gave a talk earlier in this program talking about computational issues, and there's been also a bunch of others like In et al. And Montesor et al., and I'm sure I'm missing some because this is a very fast growing area where adversarial generalization bounds have been given. Okay, and what we have been looking at is, and the way our work is somewhat different, is that we have been interested in non-parametric methods and how they respond to adversarial examples. Okay. Okay. So let's get to that. Okay. So in particular, we've been interested in nearest neighbors, and we started looking at when is nearest neighbors robust to adversarial examples. Okay? And here is something that we could show. So what happens with one nearest neighbors, right? So what we can show is the following. If your mu, remember mu is the distribution over x, if your mu is continuous, and if in a neighborhood of x, your eta is not 0 or 1, right? So it lies somewhere between 0 and 1, then the robustness radius at x basically just converges to 0 as n grows, right? And what does this imply? Well, basically what this implies is that the distributional robustness of one nearest neighbor, at these points, it's just basically 0, right? And of course astuteness as well, right? So the distributional robustness at this point is basically 0. As n goes to infinity, the robustness radius actually decreases, right? And this is somewhat in contrast with accuracy, which still might be high, right? If your eta is like 0.99, your accuracy might still be pretty high because your accuracy will converge to twice eta times 1 minus eta, but your distributional robustness won't be. Right, your distributional robustness would really go to 0. Okay, and here is some proof intuition, which is also not super duper hard to see. So what's going to happen over here, right? So what's going to happen is that as n grows, as you get more and more points, if you look at a ball of radius r, right? You have your x and you have a ball of radius r around x. If eta is not exactly 0 or 1, this ball will have some point which has a different label than x, right? So if your x's label was 1, you will get at least a point whose label is 0. And this point is an adversarial example, because if you place a test point right at that, that's going to be its nearest neighbor, and that's it, right? So, for one nearest neighbors, you can't really expect it to be robust at all. Okay? And the similar argument will also hold for constant k. So there, you have to look at majorities and stuff like that. Things have to be a little bit more complicated, but it will still hold for constant k. Yes, question?
So I just wonder, does it apply when the dimension is very high?
It will still apply, but n has to be very large. Right? So if your n is, you're absolutely right. So you will probably need n that is exponential in the dimension, right? Because then your points have to come closer and closer. But as n goes to infinity, the limit will still be 0. Okay. Any more questions? Yes.
So is this like saying that really the best robust classifier that you can hope will have robustness 0 or what?
Excellent question. So, so in these regions, what I'm saying is in these regions, if you use k nearest neighbor with constant k, as n grows and grows, the robustness will converge to 0. Even though that's not the case for accuracy. Okay, so fine. So we looked at constant k, and in constant k the accuracy is sometimes not too bad, but robustness is not that great, right? So what happens? What happens with larger k, right? Can we ever get robustness? And let's remind ourselves what happens with k nearest neighbor and accuracy, which we kind of talked about yesterday. So yesterday what we talked about, what we showed was that as n goes to infinity, the risk of one nearest neighbor converges to something like this, right? Twice expectation over x, twice eta x times 1 minus eta x as n goes to infinity. And this is, and what we pointed out is that this is more than the Bayes optimal risk, right? So remember, Bayes optimal was our, kind of gold standard classifier. And this is for accuracy, and this was more than the Bayes optimal risk, right? And we showed, so in some sense this was inconsistent, right? Inconsistent in the sense that it doesn't converge to the risk of the Bayes optimal. And what we showed was that k and n is also inconsistent for constant k, right? And then what we showed was that if k, however, if k grew with n, so if k went to infinity as n went to infinity, and k over n went to 0 at the same time, right? Then things were more and more local. Your predictor became more and more local, and k went to infinity. Then the risk of k nearest neighbor would converge to the risk of the Bayes optimal, right? So this is something we could show. So we could, we showed that when k grows in a certain manner, then things are actually not that bad. Okay, so this was something we talked about yesterday. Okay. So if you talk about the robustness of k nearest neighbor, what can you really expect, right? If your k grows, your k nearest neighbor converges to the Bayes optimal. So, its robust regions should converge to the robust region of the Bayes optimal, right? We can't really expect anything better, right? That's not going to magically happen, right? So, so the question is, okay, so that's the best thing we could expect. So let's look at where the Bayes optimal is robust, okay? So, so we are going to do that, and since this is a theory talk, let me start out by defining some notation. Okay, which yes, questions?
So in the previous theorem that you showed, you assume eta is between 0 and 1.
Yes, yes.
Does that result also hold if eta was bounded away from 0 by some constant?
So eta is probability y equal to 1 given x, right? So if eta is exactly 0, then you need
bounded away from 0 by some constant.
Oh, I see. Bounded away from 0 by some constant. I see. Good question. That's a good question. I think we use that in the proof, but I'm not 100% sure that we need it. We use it in the proof that it is bounded away from 0, you're right. But I'm not 100% sure you need it, because at least for one nearest neighbor, you just need 1 point in that ball of radius r. Right? 1 point with a different label. So, yeah. Okay, so good question. Excellent. So now, yes. So let's get back to this, and so let me start out with some definitions. So again, it's a definition that we used, we talked about yesterday as well. The probability mass. So the definition that we are going to talk about is balls of probability masses, right? Because remember from yesterday, when you talk about nearest neighbors, it's the right abstraction to look at are balls of certain probability masses, right? So the probability radius of a ball, so Rp of x, so here P is a number between 0 and 1, so P is a probability. It's essentially the radius where this ball has probability mass P, right? And this looks a little bit complicated, so forget about the ifs and so on, because you need it to get things to work out and stuff like that. But essentially what this is, Rp of x is the radius of the ball whose probability mass is just P, right? So that's all that is, right? So this is Rp of x, balls of probability radius. And then now once we have these probability radiuses, we can now define something called robust interiors, right? These are sort of analogous to what we defined yesterday, which were the actual, which were the interiors, but this is actually a little bit stronger, right? So what is the robust interior? So now we have three parameters, R, P, and delta, right? And what does this mean? So it's all points x, such that if you look at all x prime in a ball of radius r around x, and if you look at this x prime and a ball of probability mass p, right, there everything in these union would have eta greater than equal to half plus delta, right? So if you remember, p is a probability parameter, right? And delta is, like a margin parameter, right? Yesterday we talked about this half plus minus delta, right? Delta is like a margin parameter and p is like a probability parameter. And what you want here is you look at x, you look at balls of radius r around x, and you look at every point in these balls. And if you look at balls of probability mass p around those points, then in all these balls, the eta is greater, eta is, py given x is strictly greater than half plus delta, right? And so this is the positive part. And similarly, you can also define the negative part of these robust interiors. And then you can look at, the RP delta interiors would be the union of the positive and the negative, right? So so I'd like to point out a couple of things over here, right? So one thing to notice is that unlike yesterday's definition, so yesterday's definition was more in terms of averages, right? And which is good. When you are talking about accuracy, you just want the average to work out right. This definition is actually for all, right? So there's a for all over here, right? For all x prime, x double prime, and for all x prime. And unfortunately for robustness, that's kind of important because the robustness definition involves a for all, right? So you have to get them, right? The other thing to notice is that there is also this parameter r, right, which was not there in yesterday's definition. And you just kind of need this parameter r because you want things to be just sort of uniform, to kind of converge to the same label in a radius, in a ball of radius r. Okay, so now let's get back to where the base optimal is robust. What you can show is that the base optimal has robustness radius r in this particular interior, right? So the positive interior with parameters r 0, 0, union the negative interior with parameters r 0, 0, right? And this is, follows mostly from the definition. The trick is setting up the definitions properly. And then you can also set up the astuteness, right? So you can talk about astuteness, and it's, what you would expect it to be. This is, eta x times this. This is where it's robustly positive, and then this is the probability which it's positive, plus this is where it's robustly negative, this is where it's robustly negative, and this is the probability with which it's negative, right? So once you set up the definition, this is quite easy. Yes?
Can you remind me what the zero is parameterized?
Oh, yes. So the 0 here is the probability, right? The ball of, so 1, 0 is ball of probability p, so that p is 0. And the other 0 is the margin delta. So that is also 0, right? So this is the limit object, so these things are all zeros. Okay, what about k and nearest neighbors? So here is something that we could show. Suppose we have like a parameter delta n, the margin parameter that goes to 0. If kn grows in this particular way, and the growth is square root dn log n divided by delta n, and your pn, it's like a complicated expression, but think about it like this, right? Kn over n times 1 plus something, right? 1 plus maybe something else less than a constant. Then with high probability, kn nearest neighbors, and high probability there is a 1 minus delta which is hidden in various constants, which I'm not going to go into. Kn nearest neighbors has robustness radius at least r in this following region, right? So the interior with radius r, the probability parameter is p sub n, the margin parameter is delta sub n, union the negative interior with radius r, probability parameter p sub n, and margin parameter delta n. Okay? And so there's a couple of comments over here. So first is that this is actually much faster than required for accuracy, right? So of course, I mean, if you also want accuracy, then your kn over n has to also go to 0, right? So that's just, that's just given, right? So I'm not going to go into that. So that's just sort of given. But the thing to notice is that for kn, for accuracy, all you needed was kn to go to infinity, right? And this is a much faster rate of growth, right? Square root dn log n is, pretty fast, right? So this is a much faster rate of growth. Okay, so this is something to note, and we don't actually have any bounds of what happens in between. So yeah, I don't know, much faster rate of growth. Okay. The second thing to notice is if your Pn goes to, Pn is approximately Kn over n, if that goes to 0, and if your delta n also goes to 0, then this quantity, right, this interior, under various regularity conditions, of course, then this interior will also go to the robust region of the base optimum, right? So then your the interior of R, Pn, delta n, Pn and delta n are all both going to 0. Here again, Pn and delta n are both going to 0. So under, if things are nice and regular, then this this sort of thing will also go to R 0, 0. Right? So essentially, under nice conditions, this will also go to the robustness region of the base optimum. Right? So if you let your Kn grow properly, then its robustness region will go to the robustness region of the base optimal. And to be honest, that's all you can expect, right? Like K nearest neighbor converges to the base optimal. What more can you get, right? It's not magically going to be better. Okay, so let me give you a little bit of proof intuition. So why does this kind of thing happen? So the magic word over here, or the magic two words over here, is uniform convergence, right? And that is where the D comes from. So those of you in the know, you will realize that that is where the D comes from, right? So what's going to happen over here? If your Kn is this big, then by uniform convergence, what you're going to have is, if you look at x, right, and if you look at the distance to its knth nearest neighbor, right, for all x altogether in the whole world, the probability mass of that ball is going to be, Kn over n plus minus something small, right? So this is approximate. This is an approximate thing, but that's essentially what is going to happen, right? And the key here is for all x, okay? And now, if your x lies in, let's say, a positive interior, right, then for x double prime, if your x prime lies in a positive interior, then or for x double prime, which is a knth nearest neighbor of x, this eta is going to be greater than half plus delta n, and by uniform convergence, things will just work out, right? So the idea here is that your ball is big enough and you have enough Kn that you are outputting the same thing as the base optimal, which is again the same by definition of the interiors, which is again the same as the base optimal in the place that you are supposed to be robust. Okay, so that's kind of the idea. Okay, and for our proof, we actually need uniform convergence. I'm not exactly sure if you always need it, so that's kind of an open question. Okay, so if you don't need uniform convergence, then you can bring down the K. Okay, so the next question is, okay, so this is well and good, but K is really large and it will take you a long time. So can we get robustness for something like one nearest neighbor? And as it turns out, the answer is actually yes, but what you need is a somewhat modified algorithm. Okay, so to get to this modified algorithm, let's start out by thinking about when is nearest neighbor robust, right? So if you look at one nearest neighbor, when is it going to be robust at a particular x? Well, it's going to be robust when points with different labels are well separated and your x is close to a point with the same label, right? So you have an x and y, it's close to the point with another x which has the same label y, and it's far off from point which has a different label, right? So the question is, can we artificially do this, right? So you remove a subset of the training data that is basically causing trouble, right? So you remove a subset of the training data so that differently labeled points are far apart, and then you do nearest neighbors on the remaining data, right? And the question is, which are the points that you can remove? Well, you just, what points are you going to remove, right? Like there's any kind of subsets that you could remove. So you keep a bunch of points whose labels you are confident about, and then you keep, you know, a maximal subset of the rest, and then the rest will be fine. Okay? So, okay, so let's now try to formalize this. So to formalize this, let me introduce this notion of R separation. So suppose you have a set of points xi, yi, like a whole bunch of label training points. We say that these are R separated if points with different labels are at least distance 2r apart. Okay? And what we will do is, you know, so that's what we mean by separated. Right? So remember we talked about how, you know, points with different labels should be separated. The notion of separation we are going to use is R separation. Okay? And then we also talked about we will keep the points whose labels we are confident about. So how do we get these confident labels? Let's look at that, right? So here is how we are going to get confident labels. So suppose you have an input x, a training data set of size n, and parameters, you know, little delta and big delta. You set kn to be 3 log, you know, 2n over delta squared. And, you know, this is again, these are set to make the Chernoff bound work out, as you can probably tell. Over delta squared. You look at those many neighbors of x and average them, right? And if the average is between half minus delta and half plus delta, then you say I don't know, because then you are too uncertain. Otherwise, you round up this average and you return it, right? So basically, it's like a simple thing where if the you know, if you look at your nearest neighbors, if their majority is too if far off from half, bounded away from half, you say yes, and if the majority is too close to half, then you say, well, I don't know. Okay, and here is the full algorithm for all I. F of xi, so you first compute its confident labels, right, with parameters little delta and big delta. You start out with an empty set, right? And this empty set, what you're going to do is you're going to build up a set of confident points, right? And then what you do is if your confident label is y, and your confident label is equal to the confident label of everybody else in your vicinity, right? And sorry, I should have added that this is not, I don't know, right? So if your confident label is y, if it is equal to the confident label of everybody else in a ball of radius r around you, and this label is not I don't know, then you add this to your confidence set points, right? So you add this to your set of confident points, and then once you have those confidence points, you're always going to keep them, and then you return the largest R separated subset of your training set that contains these confident points, right? So you return them, and that's your training data for one nearest neighbor. Okay, you just do one nearest neighbor on this. Okay. So what can we say about this algorithm? So again, we can show something, and it's unfortunately it's a little bit more complicated. So suppose you have this delta, little delta, which is, you know, kind of one of these high probability parameters, and suppose your kn looks like this. So kn, this is the kn that we used for our algorithm, right, for the confident labeling algorithm. And your pn is kn over n times 1 plus something like square root d over kn, right? So that's about your pn. And then we are going to define this, so we are going to choose some parameter t, and we are going to define this set, right? So this set is basically the r plus t interior, right? The interiors with parameters r plus t, pn and delta n, the union of the positive and the negative interiors, where the density is somewhat high, right? And you need this somehow, at least we need this kind of high density condition, because if the density is too low, then you're not going to see points from there, right? So here the density is high enough that you end up seeing points from these regions, right? So you have, so in some sense, this is kind of the high density subset of the interiors, right? So if you look at this xr, then what we can show is that with high probability, the algorithm that we just talked about has robustness radius at least r minus 2t on this particular set, okay? So again, what does this mean? Your xr is essentially, it's a high density subset of this area, of this region, right? And you know, you need the high density subset because you need to see some of these algorithms in your training data, right? That's really motivating this thing. And then notice that as t, pn and delta n goes to 0, this also, you know, under various regularity, things are nice and regular, this will also go to the robust region of the Bayes optimal, right? And what we have is the high density region of this. So, you know, so this will also, provided the density is again high enough, then it will also go to the robustness region of the base optimum. Okay, so what's going on over here? So let me give you just some brief proof intuition. So what we can show is if your xi lies in this interior, right, in the right interior, and your yi is the right label for xi, then based on the properties of k sub n, right, because k sub n is large enough, you can do large deviations, you can show that, the right things will happen and xi yi will get added to the confidence set, right. So if your xi actually lies in the interior and your yi is the right label, it will get added to the confidence set, right. On the other hand, if you have a particular point, test point in XR, by uniform convergence, there will be some xi yi in your training set and close to x, right. So imagine this is your x, there is going to be some xi in your training set that is also close to x, right. And this comes from the fact that it's in the high density region, right. If this was not in the high density region, this training point may not be there and you may have made some mistakes, right. And then from what we talked about, this xi yi will actually get added to the final training set, right. So if this xi yi gets added to the final training set, then you are doing the right thing, right. Now, so what this means is that if that x is an xr, then you are going to output the right label for it, right. On the other hand, since your t is R separated, right, and the final thing will also be R t and the final training set is R separated, any xj which has a different label is going to be at least 2r apart from this, 2r apart from this xi. So this distance is going to be at least 2r. So this distance will be at least, 2r minus t. And if you have another x prime, which is also going to have the same label as xj, that distance is going to be at least 2r minus 2t, right. And so what we can show is that by various triangle inequality style arguments, what we can show is that this will give you a radius of at least r minus 2t, right. The robustness radius will be at least r minus 2t. Yeah. Okay, so so far we talked about this algorithm. Now the question is, how does it actually work in practice? Because we showed various large sample convergence rates. In reality in life we have finite samples. How does it work, right? So we looked at some experiments. We looked at standard 1 nearest neighbors. Robust NN is our method, and we looked at 2 standard adversarially trained nearest neighbors. So at that point there were no other defenses. So we looked at adversarially trained nearest neighbors, and we looked at a few different data sets. And so the kind of attacks we used were, so we had a couple of standard baseline attacks. So the first one is the direct attack. At the time this was the only attack known for nearest neighbor. So this is 2018 we are talking about. So basically the idea is that you find the closest x prime in your training set which has a different label and move a distance r towards it, right. And then there was also something by Paperno et al. Where basically you find the kernel classifier which is just soft nearest neighbors and you just attack it with standard gradient based methods, right. So for parametric methods there are just all kinds of gradient based methods for attacking them, so you just use those, okay. And these are some of the attack results. So what you see here is robust NN is us, right. So this is the orange line is ours. So in the x-axis what you have is the max L2 norm of adversarial perturbation. In the y-axis what you have is classification accuracy, right. And so if the accuracy goes down, that is not that great. If the accuracy remains up, that's kind of a good thing. And what you see is that this the orange line mostly just stays above the rest, right. And standard nearest neighbor is not very good, and adversarially trained nearest neighbor, which is actually a very good defense for parametric methods, is in fact not that good either. Okay. There is also another line of work on what are called black box attacks. So in black box attacks, what happens is, instead of attacking the particular classifier, you build another classifier on the training data and you attack that, right? And the reason that is interesting, I mean, this is of course a weaker attack, but the reason why that is interesting is because a lot of parametric defenses, early defenses, what they would do is they would mask the gradient, right? So they would just somehow hide the gradient, and so the gradient based attacks for white box attacks would not work, but these black box attacks would work extremely well. So it's a weaker attack, but it works better because of the way the attacks are constructed, right? So that's why these are also interesting to look at, right? And so what we see is that the black box attacks, everything is more or less the same. And the reason for this actually, so we used two substitute classifiers. So one was a kernel, like soft nearest neighbor classifier, and then the other was a neural network. And the reason for this actually is that black box attacks, they translate very well from one neural network to another, but they don't translate that well between parametric and non-parametric. And this had been observed before. I mean, we are not the first people to make this observation. This had been observed before, but this is just a sanity check. So this corroborates past results, past experimental things that people have seen. Okay. So yes, great.
You're almost done.
Okay. So what we did was, we just, showed some robustness properties of nearest neighbors. We talked about a new nearest neighbor, robust nearest neighbor algorithm, and we gave some experimental results. Okay, so this was, kind of the first part of the talk. Okay, yes.
Is your defense related to smoothing, that I can say add a Gaussian noise in my test time and look at the majority of the labels that I'll collect from the
not that I can see. Not that I can see, but I think it would be nice to see if there's a connection. Okay, so yes, sorry.
You mentioned that the adversarial attacks from parametric don't necessarily translate to non-parametric. Do they in the reverse direction?
Well,
you take something black box that treat it as not
that we have seen on our experiments. But I can't remember our reference which does it. Yeah, actually probably not. So the Papernose paper probably also shows that. I think I have to look. I have to just double check the the results. But that is also my guess. Okay. So so we talked about nearest neighbor. Yes, sorry. Yes.
So going back a couple slides, for the black box attacks, in the bottom you've taken a neural network architecture, trains it with presumably cross-entropy loss, and controls an L2 adversarial perturbation on MNIST, and evaluated using nearest neighbors. That's my understanding of this book.
Right, that's correct. Yes.
So this is a very small L2 perturbation, all things considered. Most things in MNIST I'd expect to be.
Right, excellent question. So these are normalized.
These are what?
I think they were normalized.
To what? Like, what is the scale here?
I'll have to look up the exact details, but this is not 4 pixels. This was normalized. So is that what you're asking,
Well,
or?
if I have like any two MNIST images are more than 4 distance apart in L2 norm.
Yeah.
So the fact that if it's that scaled, and the fact that you're getting 100% accuracy on even standard nearest neighbors isn't terribly surprising starting from the test set.
Right. No, I agree with you, but these were, this is not the standard MNIST scale. So these were normalized. I don't remember the details off the top of my head, but I can look it up for you. Right, I mean, it's not 4 pixels. So when I say 4, I don't mean 4 pixels, right? Like 4, that's not the scale. Okay. Okay, so now coming back to, right, so we talked about nearest neighbors. The next question is, can we just kind of look at more generic non-parametrics, and this is some work that we that we just did, and it's it's going to come up in archive in a few days. So the idea is that can we get generic attacks and defenses for non-parametrics like nearest neighbors and decision trees and random forests, right? So and the reason why we care about these generic things is for parametric methods we do have generic things, right? So we have a lot of gradient based attacks. So there are also other other kinds of attacks, so that's why I said most, but we do have a lot of gradient-based attacks where, remember in parametric models, you get theta star by minimizing a loss function. So the gradient-based, you start at some x and then you go up the loss function until the label changes, right? So, things like fast gradient sign methods and stuff, they're based on this sort of thing. And then there's a lot of others, right? But basically this is kind of the idea, right? And then kind of defenses that work are, what is called adversarial training. A lot of defenses are like this. So basically what you do is training with data augmented with adversarial examples, right? And people have been doing this for a while. I think Alex Madri's group has a very nice paper which offers some theoretical justification for it. But there's many, many others, right? So have been doing this for a while, right? But for non-parametrics, what happens is prior work has, there's been a fair bit of prior work. So they have either looked at specific classifiers, like nearest neighbors or decision trees and random forests, but there is nothing that generic. And the challenge is that the gradient-based attacks, they don't really apply. I mean, you could approximate things and then you could look at the gradients, but it's not nice, not as clean. And what people have seen, and this is not a new observation, others have seen this as well, is that adversarial training, you just saw this, but others have seen this as well, is that adversarial training does not really work that well, right? So the question is there something generic that we could do, right? So what we'll do is next we will talk about generic attacks, then we will talk about kind of some theory, a limit object, and then that will motivate a generic defense. Okay, so what is a generic attack on non-parametrics? So one key observation that we make is that many non-parametrics, so things like nearest neighbors or decision trees or random forests, they tend to be piecewise constant on polyhedra, right? So for example, nearest neighbors is piecewise constant on the Voronoi cells. K nearest neighbors, for K nearest neighbors, there's something called a ordered K Voronoi diagram, and these will be piecewise constant on those cells of those diagram. Decision trees are piecewise constant within their particular cells, and so on and so forth, right? And what we could do is we could exploit this to come up with a region-based attack, right? So what we do is, suppose your polyhedra are P1 to Pn, where the predicted labels are Y1 to Yn, right? Now what you do is you're given an X, you find the closest point on the closest polyhedra that has a different label, right? And that's your adversarial example. And if you try to solve it, it's a convex program. And if you manage to solve it correctly, or exactly, then the solution is an optimal attack, right? Because by definition it's optimal, the solution will give you an optimal attack. The challenge is that in many cases you may not be able to solve it, right? Because you will have too many polyhedra. For example, if you're looking at K nearest neighbors, there would be n to the K polyhedra, right? So what you could do is you could do some approximation. You have some heuristics for ruling out some of the polyhedra. So something you could do is, for example, you can only search over polyhedra with a certain number of training points closest to X. So you look at X, you look at maybe its 50 nearest neighbors, you look at all polyhedra that has these neighbors, otherwise you just don't look at it at all, right? And in this case you will lose optimality. Of course, that is there might be another polyhedra which has your closest adversarial example, but it's still sort of valid. Okay? So and we call this the approximate region-based attack. Okay. Okay, so this is fairly generic sort of attack. What about a defense? Okay. So so to do a defense, yes.
Do we usually assume that the adversary has access to the model?
Yes, yes. In this case, the adversary does have access to the model. So that's the white box attack model. Okay, so now, so remember when we talked about nearest neighbors, we started talking about, yes, more questions?
Your region-based attack, that's a optimization in a Voronoi cell.
Yes.
Correct?
Yes.
That actually exists in the literature.
I know. Yeah. So I think there is somebody in the, I don't know about optimization in a Voronoi cell, but we realized after, after we came up with this is that people have looked at it in the context of ReLU networks. And what they do is, because ReLU networks you can also look at, piecewise constant polyhedra, right? So So anyway, so the question is, so you know, we talked about how things converge to the base optimal, and the base optimal is the best thing ever for accuracy, right? And now the question is that what would you do for robustness, right? Is there a robustness analog to the base optimal, which would be the best thing for robustness, okay? So remember earlier in this talk, we talked about astuteness, and the astuteness of a classifier f at a radius r was defined as the following. So this was defined as the fraction of points where the classifier is accurate and it's robust, right? So, and the goal of robust learning was sort of maximizing astuteness, okay? So let's try to see how we can maximize astuteness, right? If we can find the limit object that maximizes astuteness. So you start out with a robustness radius r, right? And you start out with a classifier f that predicts, and suppose you have a classifier f which predicts label j in a subset S sub j and is robust in that subset, right? Now, since you are going to be robust, what you can say is that the distance between pairwise distances between these subsets is at least twice r, okay? And then you can, and if you have these classifiers, then you can also, you know, write down its astuteness. And its astuteness is the following. You sum over all labels, j going from 1 to k. You integrate over x in S sub j. Probability, what is the probability that the label is y, the label y is j in x sub j times mu of x dx, right? So this is basically the accuracy in the set S sub j, and you sum over all such j. Okay, and this suggests the following classifier. You maximize, so you pick your subsets S sub j to maximize this particular accuracy, right? Subject to the following constraint that the distance, the pairwise distances between Si and Sj is at least twice r when j is not equal to I, right? And what you do is once you have found those Si's and Sj's, you predict label j if your distance from S sub j is at most r, right? So then you predict label j, otherwise, you know, that's it. Okay, so the thing to observe is this is very much a limit object, much like the base optimal, right? Because you need to know mu, which you never know, and you need to know, you know, this is basically your eta, right? You need to know the conditional distribution, which also you never know, right? It's kind of a very complicated thing. So can you get a finite sample approximation to this? And you can by approximating S sub j by a subset of training examples, right? So what you're going to do is instead of this particular objective, which involves your eta and your mu, you are going to look at, you know, now your S sub j is a subset of your training examples. This becomes sum over, you know, xi is your training examples is in the set S sub j, the indicator of yi equal to j, right? And you still have this condition subjected to Si, distance between Si and Sj is at least twice r, right? And if you look at it, you know, if you stare at it for a couple of minutes, what this is essentially this is the maximal subset of training samples where points with different labels are at least 2r apart, right? So if you stare at this for a while, this is what will emerge. Now the question is how to find those training samples. Actually, in the binary case, this will reduce to some sort of matching problem. And in the KID case, it's not, you know, not matching anymore. It's some sort of graph independent set, but you can still have a greedy algorithm, right? And the thing to notice is that this is actually different from what we talked about at Wang et al. You know, in our, so this is basically our ICML paper. So this is what we talked about a little bit earlier. And the difference is that there's no confident points, right? In Wang et al, what we were doing is we were saving a bunch of confident points, and then we were picking a maximal subset of the rest. Here, there's no confident points. We are just picking the maximal subset. Okay. So this automatically suggests an algorithm. You find this maximal subset, right, where they're 2 or more apart, and then you just build your favorite classifier on it, right? You can build nearest neighbor, decision trees, random forests, and so on, right? So that's your algorithm. Okay, and we call that adversarial pruning. Okay, so now I can show you a few experiments. And what we were trying to understand is, you know, of course, how good is this region-based attack? How effective is adversarial pruning as a defense? And, you know, does it work for parametric as well? Okay. So how do we measure attacks? Because we will evaluate a bunch of different algorithms, we are going to use this notion of an empirical robustness, right? So the empirical robustness is essentially the distance to the closest adversarial example produced by A on F at X, right? So this is the empirical robustness of an attack on A at X, and basically our attack metric is going to be average empirical robustness over examples where F is accurate. So if it's a small, that means your attack is better, and for optimal attack, this would be the average robustness radius, right? And the average being taken over the accurate points, okay? And we looked at, 4 different kinds of classifiers, nearest neighbors, 2 kinds of nearest neighbors, decision trees and random forests. We looked at 9 data sets. I won't, bore you with all 9. And then we had a bunch of attack baselines. So the current, I think the current kind of state-of-the-art black box attack is due to Cheng et al. And we looked at that for everything. We looked at, for nearest neighbors, we looked at direct attacks and kernel substitution attacks. For decision trees, we also looked at, so there's an attack by Paperno et al. For decision trees, we looked at that. And for nearest neighbor, one nearest neighbor in decision trees, we use our exact region-based attack, and the approximate one is for 3 nearest neighbors and random forests. Okay. So here are some results. So what you see here, low means better, right? Like generally a low bar is not a good thing, but here low bar is a better, means better. And what you see over here is that the direct attack is kind of not that great for 1 nearest neighbors, and the black box attack is actually pretty good. The kernel attack is also not that great, and RBA exact is kind of the best. Similarly, for 3 nearest neighbors, RBX approx is, for this particular data set, RBX approx is also the best. For decision trees, again, this is the best, RBA is the best. And for random forests, again, we are using RBA approx, it's a little bit better than the black box, okay? And so usually what we find is that the RBA exact turns out to be the best. The RBA approx, we find it to be a mix. On some data sets it's better, some data sets it's a little worse than the black box. And this is not too surprising because it's doing an approximation, and if we did a more accurate approximation, it probably would have been better, right? And it's not super surprising. Okay. So for defenses, what we would do is we would look at the empirical robustness of a defended classifier over the empirical robustness of the undefended classifier. So that's kind of our defense score. So high defense score means the defense is actually, it's good, right? And if you have like a standard undefended classifier, then its defense score should be 1, okay? And here is here are some results. So here the high bar is a good thing, right? Here higher means better. And what you see is here, okay, so for 1 nearest neighbor, we looked at undefended, which is 1, adversarial training, Wang's classifier, which is our previous thing, and also adversarial pruning, right? And what we found overall is that these are mostly comparable. Sometimes adversarial pruning does a little bit better, but these are mostly comparable because they're doing, fairly similar things, right? It's not that surprising. For 3 nearest neighbor, we again look at undefended adversarial training and adversarial pruning. In this case, obviously adversarial pruning is better. For decision tree, there is a new robust decision tree attack by, I think by Cheng et al., which just came out in ICML 2019. So we compare with them. The results are mixed. Sometimes they are better, sometimes we are better. This is one data set. And for random forests also it's a mix. So their defense also applies to random forests. It's also a mix. It's I would say competitive, not necessarily better, right? And again, here you see that the trend has reversed. RS is better than adversarial pruning, but adversarial pruning is more general, right? So here again, RS and adversarial pruning are pretty close. Okay. Then finally, another question is, what about adversarial pruning for parametric models, right? So there, again, we looked at, these are 2 data sets. We looked at logistic regression and multi-layer perceptron. And what we find is, again, there, adversarial pruning does help a little bit, but adversarial training, as expected, is actually much better for parametrics. Okay. In conclusion of experiments, so what we see is that the region-based attacks are, either better than or competitive with the prior work. Adversarial pruning is, either better than in some cases or competitive with existing defenses, but of course it's more general. And then it also helps parametric methods, but not as much as adversarial training. And the real question is, what is going on, I think. Because there must be some fundamental difference in which parametric and non-parametric methods look at data, and which results in this difference. And I think the real question is, kind of what is going on, right? So in conclusion, we can show that Kn nearest neighbors in general can be made robust to adversarial examples when your Kn is very large. You can have some modified nearest neighbors which is more robust, but the more interesting thing that we see here is that non-parametric methods are actually somewhat different from parametrics when it comes to adversarial examples. And I think the real questions for theoreticians is, what's going on. And these are, finally, these are my colleagues. Ishen and Yao Yan, these are my students, and Ishen and Somesh Shah is my colleague. Cyrus is a postdoc at UCSD. So Ishen and Somesh are co-authors on our last year's ICML paper about the nearest neighbor, nearest neighbor stuff. And Cyrus, Yao Yan, and Ishen are responsible for the newer work. And with this, I will stop.
So after you find the SJs, is it guaranteed that for every X there will exist SJ which is distance less than R?
Not necessarily.
The prediction rule depends on that.
Yeah. Yeah, they may not exist. Yeah, you're right.
What is when it does not have a...
So then what would happen is that, you would never predict that label. It's not a good classifier, but you would never predict that label.
Perhaps you said this and I missed it, but is there a cost that you pay in pure accuracy for implementing these robust methods?
That's an excellent question. So you do pay a cost in accuracy. Yes, you're absolutely right. So that, and there should be, you're absolutely right that there should be like an accuracy robustness trade-off. So the way we are getting around this, so it's very hard to deal with by criteria stuff. So the way we are getting around it is we are just looking at astuteness, right? So we are saying that we'll just maximize the fraction where things are robust and they are, and they're accurate. You're right, yeah. Yes.
So if I'm understanding this right, you're considering k-nearest neighbors and submetric as well as perturbations in that same method?
Yes, you're absolutely right,
so
yes.
Does the necessary k you need, for example, if you're doing like L2 k-nearest neighbors and are allowing for L infinity perturbations, does the k get much larger or?
That is a very interesting question. So I believe there was, one of the papers I talked about, the linear classifier results. So that's, for them that is the case, right? So they need more data for robust optimization because, for robust generalization, because the perturbations are in different, like the natural metrics for Gaussians is L2 and then the perturbation is in L infinity. But we haven't looked at that. That's a very interesting open question. Yes?
So you're presenting this like trade-off, this like, gap between small constant k and asymptotically larger k for robustness. The eta not equal to 0 or 1 is a really crucial assumption here, correct?
Yes, that's
in the case where like it's 0 or 1 nearest neighbors is robust for
robust provided the decisions
separate,
regions are separate enough. Yes, that is an excellent point. That is absolutely right. Yes.
So going back to the initial motivation for considering these problems, does it ever make sense to compromise on the accuracy to get more robustness?
Okay, philosophical question. I think it depends to some extent on your application, I think. Right? For some cases, okay, so what I really think is what makes sense is for you to say, I don't know. right? So if you cannot predict robustly, you just say, I don't know, and then somebody else looks at it. Yes?
Is there a way to enlarge the original feature space so that you probably can achieve better accuracy and also robustness?
That is also another excellent question. So what he's asking is there a way to enlarge the feature space? I don't know. I think for certain applications that might be possible. But again, it depends on the application. Excellent question. These robustness questions, these are very, very new. People are just starting to study it. Yes?
So in the image examples, is the metric on the pixels? Because
yes, it's the metric on the pixels, yes. People have also looked at more complicated perceptual metrics as well. So there's some work on that as well. Yes?
So is it efficient to get a maximal R-separate subset? Because in any cases, those the data being tangled together, then you cannot get the guarantee they are two R-separate.
So it's for binary labels, it's a bipartite matching problem. And if your data is like different labels are entangled, then what you're doing is you're just removing the minority label, essentially. That's what you're doing, right? So let's say your eta was, let's say 0.25, right? So then, you have this region, 75% are plus and 25% are minus. And what you would end up doing with enough samples is you would just remove the minuses and you would always predict plus, which is good because that's the base optimal. That's what the base optimal would do, and that's what you should be doing. Okay. Oh, yes. Last question.
Is it possible to apply those to the regression problem?
I don't know. That's another very good question. We haven't looked at it. That's it.
Okay, so thanks, and since this was the last talk, so thanks for coming, and for the people that asked for slides, an email will go out to all the speakers and some of the slides will be posted.